Hello students, today we will discuss the next topic, that is losses in prestressed concrete. Now all of you understood what is exactly prestressed concrete. So let me once again define the prestressed concrete. It is the concrete in which there have been introduced stresses of such a magnitude and distribution that the stresses resulting from external loading can be counterbalanced to a desired degree. Desired degree means what? While designing the concrete section, we have to decide that how much stresses can be counterbalanced. That depends on the pre-stressing force and the cable profile and its eccentricity. Well, while designing, estimation of losses in pre-stressed concrete is very important because total loss of pre-stress is 12 to 18%. It's a quite considerable amount, and hence detailed estimation is always required. So we'll see today what is exactly loss of prestress, which are the different types, and how to calculate this loss of prestress. Okay, now let's see the definition of loss of prestress. Now, the initial prestress in concrete reduces with time, and this is called as loss of prestress. That means whenever the jack is used to tension the wires, so that force is called as jacking force. After that, the stress gets transferred to the concrete, and after some time, that means some days or some years, okay, you will find that the stress which was initially transferred during the jacking phase does not remain constant over the time. So this difference between the final stress and the initial stress, that is called as loss of prestress. Now let's try to classify these losses. So this is one type of classification. In that, first type is loss of prestress during tensioning process. Now during tensioning process, that means whenever the wires are tensioned by using jack, that is the tensioning process. So this loss is nothing but loss due to friction, and this loss occurs only in post tension members. Second one is loss of prestress at the anchoring stage. It is also called as anchorage slip loss. And third one is losses occurring subsequently, that means creep, shrinkage and relaxation. One more loss is remaining, that is loss due to elastic shortening. Now this loss due to elastic shortening always occurs in pre-tension members, and it occurs when the stress is transferred from wires to the concrete. That means we can say that it is loss of prestress at the anchoring stage. And in post-tension member, loss due to elastic shortening occurs only when there is a successive tensioning. Successive tensioning means one after the other wires are tensioned. So after in successive tensioning, this loss occurs. That means it is the loss of prestress during the tensioning process. Another type of classification is immediate losses and time dependent losses. Immediate losses also called as instantaneous losses. Now these immediate losses are nothing but the losses which occurs immediately after the jacking. So in which we can have three different losses. One is elastic shortening, second one is friction, and third one is anchorage slip. Now as I told you that elastic shortening, this loss occurs always in pre-tension members, and it occurs in post-tension members only when there is a successive tensioning. Friction loss is during the tensioning of the wires, and anchorage slip, it is during the anchoring of the wires. So friction and anchorage slip occurs, these two losses occurs only in post-tension members, whereas these two losses are absent in pre-tension members. Second type is time dependent losses. Time dependent losses means these are the losses which depends on time. That means as the time passes, these losses increases. So in that there are three losses. First one is loss due to creep of concrete, second one is loss due to shrinkage of concrete, and third one is loss due to relaxation of steel. Now we'll see one by one how to calculate these losses and what is exactly the meaning of the different losses. So total 6 losses today we'll see. So first one is loss due to friction. Now again, the loss due to friction is divided into two parts. The first one is loss due to length effect, also called as wobble effect, also called as wave effect. Now length effect, wobble effect or wave effect means normally the cables which are provided moderately straight or straight cables. So during the concreting, the ducts, the alignment of the ducts gets misaligned. That means it is not exactly along the profile which was intended. So the little bit the undulations in the profile that gives friction. Okay, that is the loss due to length effect or wobble effect. So this part is considered in this equation. So it is P0 e raised to minus alpha into mu plus kx. So this plus kx, this part covers this wobble effect, and the second loss is loss due to curvature effect. Now, normally, the parabolic cables are provided in pre-stressed concrete, and the shape is the sagging shape. So whenever tension is applied at both the ends, the tendons or the strands stick to the upper layer, upper wall of the duct, and always there is a friction in between the upper wall of the duct and the tendon, and this is called as loss due to curvature effect. So it depends on curvature, and so the first part of that equation, alpha into mu, that covers this curvature effect. Now, total equation according to IS 134/1980 and according to revised code in 2012, the equation remains same. That is equal to Px. What is Px? Px is the pre-stressing force at distance x meter from tensioning end, and P0, that is the initial pre-stressing force, that is equal to e raised to in bracket minus mu alpha plus kx. Now, what is this alpha? Alpha is the cumulative angle in radians through which the tangent to the cable has turned between any 2 points under consideration. Now, this cumulative angle in radians. So, when jacking is done only from the one end, that means the tensioning operation is carried out from one end, then this alpha is equal to 2 theta. What is theta? Theta is the angle made by the cable profile at the near the support. So it is 2 theta, and if jacking is done from both the ends, then this alpha is equal to theta only. Mu is coefficient of friction. So in the next table, the coefficient values for coefficient of friction is given, that total based on the contact surfaces. Well, now P0 is the pre-stressing force at the tensioning end. K, it is called as wobble correction factor, and X is the distance from the jacking end. Let me go to the next slide. Okay. Now, the value of mu and k, these are given below, and as per the type of the material. So when it's a type of high tension steel, so wire cables and uncoated stress radial strands. So for bright metal, the value of k is given as 0.0091. For galvanized, it is 0.0046, and so on. The value of mu, that means the coefficient of friction, that is given as for bright metal and wire cable. So friction in between these two materials, it is 0.25. Then for galvanized, it is 0.2. For lead coated, it is 0.18, and similarly the values are given for the uncoated stress relieved strands. So these are the values which we can substitute in the equations for friction. Now, which are the methods to reduce friction loss? Because friction loss due to friction is quite higher, and if you apply these methods, definitely we can reduce this friction loss to a considerable extent. So the first point is making the bends through an angle as small as possible. That means if you reduce the angle of bend, obviously the friction loss will reduce. Avoiding double curvatures, particularly double curvatures are required in the continuous beams. So in continuous beams, when at midspan the sagging nature is provided, and for the hugging bending moment, hugging nature is provided near the support. So there double curvature is provided. So instead of providing double curvatures, we can have cap cables, separate cap cables at the support, so that considerably reduces the friction loss. Then making the radius of curvature at bends as large as possible, so just avoid sharp curvatures. Then using the lubricants of unbonded concrete. Well, lubricants means we can add these lubricants into the concrete to reduce this friction. For bonded concrete, water soluble oils can be used, and this lubricants is flushed off with water afterwards. So such lubricants are available in the market. The pre-stressing the wires from both the ends. Yes, this is the very common method and very simple method. So pre-stressing the wires from both the ends, that means if you pre-stress the wires from both the ends, obviously loss due to friction will occur up to the midspan. Maximum loss will occur up to the midspan. When maximum loss will occur at the midspan, obviously the friction loss almost will get half. And over tensioning the wires, little bit over tensioning of the wires can help while reducing the friction loss. Well, the second loss, that is loss due to anchorage slip. Well, whenever the wires are tension, and now the friction grips, the wedge grips, these are used to lock the wires. That means some anchoring devices are used at the ends. So always there is a little bit slip at the anchoring devices. That slip may be 2 mm or 3 mm, but that provides the loss due to loss of prestress. Okay, how to calculate that? So it is E suffix S. So it is nothing but modulus of elasticity of steel, or also called as Young's modulus, into delta. Now delta is the slip. As I told you, it is maybe 2 mm or 3 mm, and that divided by span L. Now length is L is nothing but the length, total length. Now obviously, since L is the denominator, obviously for long members this loss is very less, but for short members loss is higher, because this delta is the fixed value, is the definite value, and hence span of the beam matters. That means for long spans, percentage loss due to angular slip is always lower, but for short members it is always higher. The next loss is loss due to elastic shortening of concrete. Now, in pre-tension members, this loss always occurs. In post-tension members, there are two cases: simultaneous tensioning, no loss occurs, and successive tensioning, loss occurs in the previously tensioned cables. That means one by one, when the tensions are cable, okay, when the first cable is tension, there is no loss. When second cable is tension, there is loss in the first cable. When third cable is tension, there is loss in the first two cables. That means the cable which is tension initially undergoes maximum loss of stress, and the tendon or the strand which is tension at last undergoes very small loss of zero loss of prestress. Okay, so this is the successive tensioning. Well, loss of prestress due to elastic shortening is given by the equation alpha E into Fc. What is this alpha E? It is called as modular ratio. So it is nothing but Es upon Ec. So is the ratio of modulus of elasticity of steel to the modulus of elasticity of concrete, and Fc is the stress in concrete at the level of steel. In the stress calculation, normally we calculate the stresses at the extreme top layer or extreme bottom layer, but for the determination of this loss we need stress at the level of steel. So normally at support for the parabolic cables, the steel may be above the neutral axis or above the central axis, and at mid span it is below the central axis. According to you have to consider the position, and you have to calculate this loss, the prestress at the level of steel. Well, now the next loss is loss due to shrinkage of concrete. Now, loss due to shrinkage and loss due to creep. What is the difference? Actually, they are same in both the cases. Loss is because of reduction in volume of concrete, but the reasons are different. When we say shrinkage of concrete, it is due to loss of moisture, and when we say creep of concrete, so creep is due to sustained loading. Now, as per IS 1343, the determination of shrinkage loss was very simple. It's simple. Loss of stress is equal to epsilon suffix Cs into Es, where epsilon suffix Cs is the total shrinkage strain. Now, for pre-tension member, the total shrinkage strain is given as 0.003, whereas for post-tension members, epsilon Cs is given as 0.002 divided by log to the base 10 of T plus 2, where T is the age of concrete at transfer in days. Well, so T is considered here, but according to revised code, there are two terms which you have to understand here according to revised code. One is absolute humidity and second one is relative humidity, because what are the equations are given by the code, in that relative the value of the coefficient depends on relative humidity. Well, what is absolute humidity? It is just referred as the humidity, and it is the measure of actual amount of water vapor to the in a particular sample of air measured as a mixing ratio. So it is gram water vapor per kg of dry air or mass upon volume. But we don't use this term absolute humidity. We use this term relative humidity. Now, relative humidity is expressed commonly as the percentage value and is the ratio of actual amount of water vapor present in a sample. That means it is the absolute humidity to that amount that would be needed to saturate that particular sample. Now, in other words, we can say that it is the percentage of moisture against the highest possible level of moisture in the air at specific temperature. So relative humidity is higher at low temperature because cold air holds more water vapor than the warm air, and it is measured by hygrometer and known as percentage RS. So in IS code you will find percentage RS is the wording which is used. Now again, two more terms you have to understand here. That means this is actually the uh, it is actually the shrinkage strain is divided into two strains. One is autogeneous shrinkage and second one is drying shrinkage strain. So what is exactly autogeneous shrinkage? So autogeneous shrinkage is an important phenomena in young concrete. That means it occurs during the initial days only at low water cement ratio, that is when the water cement ratio is particularly less than 0.42, all the water is rapidly drawn into the hydration process, and the demand for more water creates very fine capillaries. The surface tension within the capillaries causes autogeneous shrinkage, which can lead to the cracking. Well, this autogeneous shrinkage can be avoided by keeping the surface of the concrete continuously wet. Okay, so here the T term is used in which when the curing is stopped. Okay, so that is the T term. Well, with wet curing, water is drawn into the capillaries and the shrinkage does not occur. Okay, so this is the method to avoid autogeneous shrinkage. Well, what is drying shrinkage? Drying shrinkage is defined as the contracting of hardened concrete mixture due to loss of capillary water. This shrinkage causes an increase in tensile stress, which may lead to cracking, internal warping, and external deflection before the concrete is subjected to any kind of loading. That means the cracks occur or the external the deflection occurs even the member is not subjected to any loading. So this is due to drying shrinkage. Well, now how to get the autogeneous shrinkage strain and drying shrinkage strain, that we'll see in the next slide. Well, so these are the tables which are given in IS 1343/2012. So loss of stress is given by epsilon CS into ES. Okay, so this value of total shrinkage strain epsilon Cs, which is required here in this equation, that is given by epsilon CD plus epsilon Ca. Well, so epsilon Cs is the total shrinkage strain, epsilon CD is the drying shrinkage strain, and epsilon Ca is the autogeneous shrinkage strain. So both separately we'll calculate. Now, according to grade of concrete, the values of autogeneous shrinkage are given here. So for M30 it is 35. Now it is epsilon Cs into 10 raised to minus 6. There is a printing mistake in IS code, so it is 10 raised to minus 6. Well, drying shrinkage strain is given by epsilon CD infinity. That means is the for the total value of the drying shrinkage strain. It is kh into epsilon CD. What is kh? So actually kh, that value depends on the H0 value, and H0 is the notional size. So for 100 the kh value is 1, for 200 it is 0.85. What is that H0 notional size? Notional size is calculated as 2 into AC divided by U. So AC is the cross-sectional area and U is the perimeter of the concrete. That means this value depends on surface area actually of the concrete. So it's the ratio of total perimeter divided the ratio of total cross-sectional area divided by perimeter. That is H0. Now the another term, that is epsilon CD, it is given by this table. So epsilon CD depends on percentage humidity, RH value. So for 50%, these are the values given for different grade of concrete, and for 80% RH, these are the values which are given for the different grade of concrete. So in between grade of concrete we can do interpolation. Such a note is given by the code. The values for the other designated grades may be obtained by interpolation. Okay, so we can substitute the value of autogeneous shrinkage in this equation and the drying shrinkage from this calculated from this table in this equation, and we get loss of stress due to shrinkage of concrete. Now this is total loss of shrinkage due shrinkage of concrete. Now if you want to calculate the exact value of shrinkage strain with time, so you have to introduce the term T. So epsilon Ca, this is autogeneous shrinkage, is the function of time since the bracket T is given. So that is beta suffix As of function of time into epsilon Ca. Now epsilon Ca that we can calculate from the previous table, and beta Ast, this is the new term, and for that this equation is given. So 1 minus exponential minus 0.2 under root of T. So where T is in days. Now what is this T? So it is T is the age of concrete at the moment considered in days. That means after how many days? After 28 days, after 6 months, after 1 year. So in days we have to substitute that value in this equation. Okay, and This is the multiplication factor to this drying autogeneous shrinkage strain. Similarly, for drying shrinkage, we have this another equation, epsilon CD T is a function of time. So epsilon Ts T comma Ts. So what is T comma Ts? So T is again the age of concrete at the moment considered, and Ts is the age of concrete at the beginning of drying shrinkage in days, and normally this is at the end of curing at the end of curing. That means when up to the time when curing is going on, obviously the shrinkage will not occur, and after that the shrinkage will start. So that factor is considered in this equation. Now here epsilon CD is given as beta ds T into Ts multiplied by Kh into epsilon CD. So Kh into epsilon CD that we saw in the previous table, and this is the additional term, and which is given by this equation. So in this equation we can substitute the values and we'll find the drying shrinkage with time. So we'll substitute both these values in the earlier equation, that is epsilon Cs into Ks, okay, and we can find the shrinkage strain and the loss of pre-stress due to shrinkage after some 20 days or 60 days or 180 days. So time, according to the time we can calculate. Well, the next loss is loss due to creep of concrete. Now as per IS 1343/1980, the simple method was given, that was creep coefficient method, which is given as phi into Fc into alpha E. So phi is called as creep coefficient, and the values are given like this. For 7 days the value is 2.2, for 28 days the value is 1.6, and 1 year it is 1.1. Fc is the stress in concrete at the level of steel, and alpha is the modular ratio. Well, it was a quite simple method, but according to the new code, the creep coefficient method is used, whereas the equation remains same, but the calculation of creep coefficient is little bit quite lengthy. Now here again we'll see three different forms of the equation. One is approximate loss due to creep of concrete. Second one is the perfect, that means exact loss of stress due to creep of concrete, and the third one is after some time, that means according to the time we can calculate creep. So all these equations we'll see here. Now creep coefficient phi is given by the equation phi 0 beta into beta is the function of T comma T0. So what is this T? So T is the age of concrete at the moment considered, and T0 is the initial time of loading, that means when the stress is transferred to the concrete. So phi 0 is the notional creep coefficient, and beta, so this value we will calculate. Now where precise calculations are not necessary, phi 0 can be considered from the table. So this table is given in the next slide. Substitute to condition that compressive stress does not exceed 0.36 FCK. So this is the value which we consider in the stress block at the age of loading, and mean temperature of concrete is in between 10 degrees Celsius to 20 degrees Celsius. So this is the range of the temperature which is given, with seasonal variation between minus 20 degrees Celsius to 40 degrees Celsius. For temperature greater than 40 degrees Celsius, the coefficient given may be increased by 10% in the absence of accurate data. So whatever the values are given in this table, well, these are applicable for temperature 10 degrees Celsius to 20 degrees Celsius, and the variation is also given as this seasonal variation. Now in this table the creep coefficient value is given, and it depends, that varies according to the age of loading T0. So for one day what are the values for 7, 28, 90 and 365, that is for 1 year. Now under dry atmospheric condition, that means when the relative humidity is 50%, and the second the part is given as when the relative humidity is 80%. So under relative humidity 50 and 80, under both the conditions the notional size is given, that is 50, 150 and 600, and for the intermediate values we can do interpolation. Well, so according to notional size and the atmospheric condition, we have to choose the creep coefficient from this equation, substitute in the previous equation, and get the loss due to. Now this slide describes the precise calculation of national creep coefficient. So in the precise calculation, phi RH into beta in bracket F suffix Cm into beta T0. Now what is this phi RH? It is the factor to allow for the effect of relative humidity on notional creep coefficient, and this is the equation which is given. So this first equation is applicable for grade of concrete less than or equal to 45 Newton per mm square, and the second equation that is applicable for FCK greater than 45 Newton per mm square. Well, RH, this is the relative humidity. Now In this equation, two terms are given, that is alpha 1 and alpha 2. Well, that we'll see in the next slide. Okay, what is alpha 1 and alpha 2 and how to calculate that. Okay, well, here beta into FCM, that is given by this equation, and this is the factor to allow the effect of concrete strain on notional creep coefficient. So this is 16.8 divided by under root of FCK plus 8, and beta T0, that is the second term given in this equation, and it is the factor to allow for the effect of concrete age at loading on the notional creep coefficient. That means here effect of concrete strength is considered, and here the effect of age is considered, and that's why this term T0 is used here. So after getting the values, all these three equations are given here. We can substitute and we can find the creep coefficient, and this is the precise calculation of creep coefficient. Now, as I told you, in the equation alpha 1 and alpha 2, two different terms are given, and how to calculate alpha 1 and alpha 2. So here are the equations. So alpha 1 and alpha 2, these two values are given. Well, now in this slide, variation with time, that means if you want to calculate the loss due to creep at the end of 28 days or 60 days or 180 days, so for that we have to use these equations. Now here the creep coefficient is given by beta t into t comma t0, that means is the function of time, into phi 0. So this phi 0 already we saw in the earlier slide how to get that phi 0. Okay, now here beta t comma t0, that is given by this equation. In this equation, one additional term is introduced here, which is beta h. Now for beta h, it is the coefficient depending on the relative humidity, and here the equations are given for beta h. Well, the first equation is given for FCK less than or equal to 45 MPa, and the second equation is given for FCA greater than or equal to 45 MPa. RH, it is the relative humidity, and RH0, it is the 100. That means it is the total relative humidity, and we have to substitute RH0 as 100. Well, in this equation is less than or equal to 1500. This is the condition which is given here. That means if this value comes to be more than 1500, you consider the value as 1500, okay, as beta h value. Well, now here this 1500 is multiplied by alpha 3, and here also it is the term alpha 3. So alpha 3 is, this is the equation, 45 divided by FCK plus 8 raised to 0.5. Well, all these alpha 1, alpha 2, alpha 3 are the coefficients to consider the influence of concrete strain. Well, so as we saw, after getting this beta t comma t0, we can substitute this in the earlier equation. Phi 0 is already given to you, and this phi 0 you can substitute here, okay, and you will get the value according to the time. Okay, well, so this is how all the losses are to be calculated. Now the last loss is loss due to relaxation of steel. Now relaxation of steel is the property of the material in which due to after some time the molecular cohesion get reduced, and because of this there is little bit relaxation of the steel. Now in prestressed concrete, the stress remains constant, the strain remains constant, but there is a variation of stress. So this is the condition of constant strain under variable stress, and that's why it is called as relaxation of steel. Now normal relaxation of steel is considered in percentage, but in IS code it is given based on the experimental data, that is the relaxation loss of prestressing steel at 1000 hours at 20 degrees plus minus 2 degrees Celsius. Now depends on initial stress, that value depends. So initial stress, if it is 50% of the Fp is the characteristic strength of prestressing steel. So normal relaxation is 0 and low relaxation is also 0. But if you increase the initial stress in the wires, then slowly the relaxation increases. Like for 60% of the initial, if 60% is the initial stress, then obviously 3%, 1% like this, the losses occurs. Well, for long-term relaxation losses, above values may be multiplied by 3, and these losses, this is quite higher loss. Obviously, some guidelines given by the manufacturer were to follow, and accordingly we can reduce the loss due to relaxation of steel. Well, so that's the end of today's lecture. Thank you. In the next session, we'll see exactly how to calculate by using some the loss of prestress by using some numericals. Thank you.